Resuming our look at magnetic forces on moving charges. I noticed quickly a little typo on the previous video. I had a vector symbol over this Vy right here. That shouldn't have been there. Vy is a component of a vector, so it itself is just a scalar. Should be no harpoon right there. Okay, anyway. This time we've got a magnetic field pointing into the page throughout this region. Uniform B field into the page, that's what all these X's represent, and I have several point charges with different initial velocities, a positive one and then 3 negative charges. They all have the same initial speed, but different directions. Okay, so let's investigate the magnetic fields, focusing first on this positive point charge. So at this moment, the magnetic force QV cross B, Q is positive, V is up, B is into the page, so we would do V crossed with B, and our thumb points to the left. We have a magnetic force pointing to the left at this moment on that charge. So if our velocity is up and we've got a force to the left and there's a right angle between them, then we know that this particle is not going to speed up, it's not going to slow down, it's going to turn. It'll be turning to the left. Let's run time forward a little bit here and say it makes some sort of turn to the left, and sometime later it's located up there. And at that moment, its velocity will be to the left. Get my velocity pen. Okay, velocity is to the left. Same speed as before. Didn't speed up, it didn't slow down because the force was perpendicular to the velocity. And now at this moment, let's check the magnetic force. V is left, so V cross B. B is into the page, so V cross B. My thumb is pointing down. The force at this moment is down. Once again, they are perpendicular to each other because of this cross product right here. Whenever you cross two vectors, the result, little vector symbol on that. Whenever you cross two vectors, the result is, of course, perpendicular to the original two. So we're seeing that this force vector is always going to be perpendicular to velocity. And so this particle, not speeding up, not slowing down, continues to turn to its left. So it'll take a turn like that. And by the time it is at this location with the velocity down, same speed but new direction, we see V cross B will give us a force to the right. So our force continues to change direction here, but it'll be the same magnitude since Q, V, and B are all the same magnitude, and the angle between V and B is 90 degrees at all times. So this force has the same magnitude at all these occasions, and I think we're noticing that what we're getting actually is circular motion here. In fact, uniform circular motion, since we are subject to a force of constant magnitude that is always at a right angle to the velocity. Therefore, we're going to get an acceleration with a constant magnitude that is always at a right angle to the velocity. We're always going to get a constant inward pointing centripetal acceleration. Thus, we discover that this peculiar force law involving that cross product will always result in uniform circular motion for some particle that moves initially in a direction perpendicular to the magnetic field. This V was initially perpendicular, it stays perpendicular to the B field, and we get UCM. Let's put in this last velocity vector down there, and our force, our magnetic force at that bottom point, and we've discovered uniform circular motion. Charged particles moving perpendicular to magnetic fields tend to move on these circular paths and will spin and spin around. Let's look more at the dynamics here. Let's take this a little further. Let's say that the acceleration of our particle given by Newton's second law, so the magnetic force divided by the mass. Let's get the magnitude of these things. We see if we were getting uniform circular motion, then we can set this acceleration, this radial acceleration. The force is always radial, so our acceleration is always radial. We can set this equal to our speed squared divided by r, the radius of that circular path. In a bit, we'll try and solve for that radius, sort of predict the radius of the circular path that this particle is going to take. Okay, so the magnitude of the force comes from the magnitude of this right here. So we will have Q is positive, so this is Q, V, and B. Magnitudes of those vectors. V and B are perpendicular to each other, 90 degrees apart. V is in the plane of the page. B is into the page, so the angle between them is 90, so we don't need any sine or cosine term from that cross product. QVB over M equals V squared over R. And this we can now solve for what is known as the gyro radius of this charged particle, the radius of its circular path moving in this magnetic field. We're solving for that R right there. So comparing both sides here, I see that there's a factor of V and a factor of V that will cancel out. And so our gyro radius, R sub G sometimes for gyro radius, R is going to be given by the mass of the particle times its speed divided by the charge of it. This one happens to be positive, but to be safe, let's put a magnitude around that, and then times the magnitude of the B field. There we go. We can predict now the radius of the circular path of a particle moving in our B field. If we know its speed, we know its charge, and we know the strength of the field. Note our numerator right there also happens to be the magnitude of the momentum of that particle, sometimes a helpful relationship. And note also that the ratio of M over Q appears in this expression. Let me kind of pull that out. This is M over Q. That ratio shows up. And there's also the ratio of V over B. This is the mass to charge ratio for that particle and is often an identifying quality of any given particle. So an electron has a mass to charge ratio that is different from the mass to charge ratio of a proton or any other fundamental particle. So this value right here, this ratio, is kind of like a signature or an ID number of a particular kind of charged particle. Okay, I think we can take this even further. Let's see, if we're moving in a circular path with uniform circular motion, then we should have a period to that motion. Let's just try and solve for that here. If I go back to this expression, and I turn this around to kind of solve for our speed, V, I can set that equal to, looks like QB times our gyro radius over M, Q times B times our gyro radius, that's this guy, over M. And I can also set that equal to our circumference, 2 pi r, over the period. So let's solve this for the frequency of this repeating circular motion, the frequency at which we're circulating. That'll be the reciprocal of the period. So comparing these two expressions here, I see that between these two, the gyro radius will cancel out, and 1 over t will equal q times b over 2 pi times m. Q times b over m times 2 pi. That would be simplifying this expression right here. Note that that radius factor canceled out, and what we're seeing here is that this frequency also depends on that. This is the reciprocal of the previous ratio, so this is known as the charge to mass ratio, and it's actually the one referred to more often. So this is the very important charge to mass ratio for some particle, for this particle, times the B field strength over 2 pi. And I think what we've got here are two key relationships, one for the gyro radius and this for this frequency, which is known as the cyclotron frequency, named after a device that was an early kind of particle accelerator. And particles would be put into a magnetic field like this and spin around. And every kind of particle would have a unique cyclotron frequency. Let's highlight these key results. Here's our gyro radius equation and our cyclotron frequency equation. The more important and more fundamental of the two is this, the cyclotron frequency, which we would measure in hertz. It's more important because, look, it does not depend on the speed of the particle. So Q over m is the same for every single electron. So every single electron circulating about in this magnetic field will have the exact same frequency, just like every single proton, which has the same value of Q over m, circulating in this field will have the exact same frequency. So for every kind of particle spinning around in your field, you can measure its frequency and determine what kind of particle it is, regardless of its energy or its speed. Every particular species will have a unique frequency at which it's spinning in a given magnetic field. So speaking of many particles spinning around in a magnetic field, let's go back up here and look at these other three particles I've got, these three negatively charged particles. Let's say that in addition to having a different charge than our original particle, let's say that if this was particle 1 and these are all particles 2, particle type 2, let's say, to make it interesting, that the mass of particle 1 was greater than the mass of particle 2. So these are all the same kind of particle, but with a smaller mass. So in our equation for the gyro radius here, let's say that the charges Q1 and Q2 are the same. So these two particles have equal but opposite charges, but this was more massive. So in this formula, if they all have the same speed v, they're in the same field B, same charge, but different masses, then they will have different gyro radii when they spin. So the smaller mass here should have a smaller gyro radius, should spin in a tighter circle. So these three particles with their smaller masses should spin in tighter circles. Let's examine those circles. Okay, V cross B for this particle, V is up, B is into the page, so V cross B points left, but that particle is negative, which flips the sign of the force. So V cross B is left, but the negative flips it, so the magnetic force on this negatively charged particle at this moment is actually to the right. And we see that that one is going to spin around in a circular path like that. Just to be sure, let's test a few other moments here. Once it gets there, V is to the right. Check out that V cross B points up, but the negative flips it. V cross B points up, but the negative flips that force to be pointing down. And yes, sure enough, we're getting our centripetal force with V and the force at a right angle to each other at all those different moments. Okay, how about this one over here? This one has a different initial velocity. Same initial speed, but it's moving down instead of up. So how is this one going to move? Okay, well, V cross B once again. V is down, B is into the page. So that will give us a force pointing to the right, except Q is negative, which flips it so it points to the left. There's our initial force on this one, curving its path this way. And you can check those V cross B's to see that we get forces like this, and like that. At those various moments. Check out our gyro radii here. This is our gyro radius. That's our gyro radius. These should be the same for these two particles if they have the same mass, same speed, same charge, and they're in the same field. But the smaller radius than this one, since this particle had the bigger mass, bigger radius to its path. Lastly, this particle over here is initially moving to the right, so V cross B points down, but negative flips it, so the initial force on this one is actually up. So this particle is going to take a turn to the right, curving up this way. And it'll end up moving on a path like that, with magnetic forces like this, this, and this. And the velocities are there, and there. Okay, big picture, look at what's similar for the three negatively charged particles here. They had different initial velocities, different directions, but same gyro radii because all four of these factors are the same. Their circles are centered at different locations because they started in different locations. But note how they are all three of them circulating clockwise. And in fact, you'll note that every negative particle you put into this field, all negative particles will be circulating clockwise compared to the positively charged particle over here. It's circulating counterclockwise. So that's a key realization. If you have a whole bunch of particles circulating in a magnetic field, all the negative ones will circulate one direction, and the positive ones will all circulate in the opposite direction. Okay, one more thing to note that perhaps you've picked up on already. It's about this force being always perpendicular to our velocity. It makes me think of the work done by a magnetic force. Work done by a magnetic force. Specifically, the force given by this formula, QV cross B. So we're talking energy here, energy transfers. Okay, so the work done by some magnetic force can be found by taking the integral of that force dotted with the displacement of our particle along some path. All right, well, since velocity is dr dt, we can use that to replace this dr with v dt. This is the integral of our magnetic force dotted with our velocity times dt. Basically here, I'm just saying that dr, our little displacement vector, is in the same direction as your velocity v. Your dr is always tangent to your path, just like your velocity is always tangent to the path, so they're the same direction. Okay, so to find the work done by a magnetic force on a charged particle, we need to dot the force and the velocity. But according to this, the force, since it's defined as the cross product of these two vectors, the force is always perpendicular to the velocity. B cross B gives a new vector that's perpendicular to both V and B. In our diagrams, our force is always at a right angle to the velocity. So their dot product is always 0. Zero work is being done by that force, which is consistent with our idea of uniform circular motion. We know that this particle is feeling a force, it is accelerating, but it's not speeding up, not slowing down, so it's not gaining or losing any energy. No work is being done on this particle. This magnetic force is not doing any work because it's always at a right angle to the particle's motion. So key result here, a very general and powerful result, is that magnetic forces do no work. A magnetic force cannot do any work. It cannot transfer energy. It cannot speed a particle up. It cannot slow a particle down. All they do is just steer. Particles. So a charged particle moving in a magnetic field will be steered by the magnetic field. Its direction, the direction of its velocity will change, but it can't be sped up or slowed down. It's going to require an electric force to speed up or slow down a particle. We know electric forces can accelerate particles that in a way that adds energy or removes energy from them. Magnetic forces cannot. Okay, this is the part that I warned you about might seem to contradict your everyday experience of magnets. I mean, after all, here, if you bring these magnets close together, you'll know that they repel each other. That repulsion will cause them to speed up and they'll be gaining kinetic energy. So it seems like the magnetic force here is doing work, is speeding those magnets up as they repel. So, okay, that would appear to be in contradiction to this conclusion right here. I would say don't worry about that for now. It'll take us a while to explain this apparent contradiction, or to resolve this apparent contradiction. For now, let's just say that the forces that the magnetic forces that we're talking about are the forces on point charges. Magnetic forces on moving point charges. We're not talking at the moment about magnetic forces between dipoles like this. So this conclusion, that magnetic forces do no work, if you want, for peace of mind, you could qualify this for now and say the magnetic forces on point charges do no work. And that's perfectly true.